Alright, what's up everyone? Welcome back to Structure Free Learning. And in this video, we're going to go back to vector addition of forces using Cartesian components. And by the end of this video, you should be able to determine the resultant force of two or more force vectors using Cartesian components or rectangular components. So the question that we're trying to answer here is, given a system of forces, is there an equivalent force system that has a resultant that has the same external effect? And if you're coming from the parallelogram law, we were able to do that graphically. And now there's another approach that we can use when we use Cartesian components. And using Cartesian components just means we're going to set up a coordinate system, usually a horizontal and vertical, anything that's 90 degrees and generally following a right hand, so that we can break things up into I and j components. We would say that the unit vector pointing along the x-axis is I hat positive this way. Pointing in the y direction, we would call a unit vector j hat like this. And essentially what we're doing is establishing positive directions for the x and y, or horizontal and vertical here. And that means that the resultant could be broken up into a horizontal and vertical component as well. And here what we're doing is using the parallelogram law, but here every parallelogram is a straight rectangle because we're following that coordinate system, and we have these x and y components, and here is the parallelogram, if you will. All right, and so we could express this vector, this resultant, like this in x and y components, and then we could break it down and write it in Cartesian vector form, like frx I hat plus fry j hat. So the question is, can I relate all these multiple forces with the resultant force vector in the Cartesian vector form? By definition, the resultant force is a summation of all the forces in my system. Here it'd be like F1 plus F2 plus F3, like this. And then I could go ahead and I could break up each force into its horizontal and vertical, or I hat and j hat components. And then if I group the I hat and j hat components together, so everything that's an I hat I'm going to add together, and everything that's a j hat I'm going to group together. And what I can see is, relating back to the resultant, I can see that the sum of this right here is going to be frx, the resultant in the x, plus this right here will be fry, the j hat component of the resultant. This relationship just tells me frx can be found out by summing up all the x components, and the resultant y component calculated by summing up all the y components together. And simply from understanding vector geometry, so if I know frx, if I know the x component and I know the y component, I can use the parallelogram law and combine, and in this case it's just a rectangle, and the resulting force vector, the resultant, I can calculate from properties of a right triangle. So I know the magnitude of that force resultant will be from Pythagorean theorem, and I know the angle from geometry of a right triangle can be calculated from the inverse tangent of the opposite over the adjacent. So let's go ahead and do some examples to illustrate the ways that we can solve it. So in this problem, I'm given two force vectors, one that's 50 newtons at an angle of 30 degrees from the horizontal, and another that's 45 degrees with a magnitude of 20 kilonewtons. So in general, our approach for any of these problems is first and foremost going to be to draw the schematic and establish a coordinate system. And establishing that coordinate system means choosing an origin or 0, 0 location, and then establishing or indicating which way is positive x, positive y. And usually the origin that you're going to choose for these types of problems is going to be at the concurrent point. So in this problem, I'm going to choose this point right here as my origin. It's the concurrent point. I'm going to draw a horizontal and vertical line. I'm going to choose positive x to the right and positive y upwards. We generally follow a right hand rule so that we're all communicating the same way. Boom. like this. I want to break up each force vector into its horizontal and vertical components. For instance, F1, I'll use the color purple. We break it up into a vector triangle that looks like this. We have F1x, and this would be F1y, the y component. And we know the directions. We're really interested in the magnitudes. And from basic right triangle relationship, we know that F1y is 50 kilonewtons sine of 30 degrees. And we know that the horizontal component from cosine is 50 kilonewtons cosine of 30 degrees, like this. That's F1 broken out into components. And I can do the same for F2. And here's the horizontal component for F2, which is 20 cosine of 45 degrees. And the vertical component, which is F2y, and that would be 20 sine of 45 degrees. Yes. So I've broken out into components. Now I could choose from here to go with a vector approach or a scalar approach. So if we choose a scalar approach, the next thing that we're going to do is just sum the forces that are all pointing in the x, and we're going to sum forces that are pointing in the y. And that just means summing up all the x components together and the y components together. The x component of the resultant force is going to be, we say anything pointing to the right, as we did in this positive x direction, is a positive force. And we're going to sum forces in this x direction. And this is going to be F1x pointing towards the right. So that's a positive 50 kilonewtons times cosine of 30 degrees. And then I've got F2x, which is pointing to the left. So that's going to be a negative 20 kilonewtons cosine of 45 degrees, like this. And when I sum those up, I'm going to get 29.16 kilonewtons. And that's my result for the x component of the resultant. And then I can go ahead and do the same for the y. Anything pointing upwards is considered positive. So here I'm looking at F1y, and that's 50 sine 30 pointing up. So that's a positive 50 kilonewtons sine of 30 degrees. And then F2y is also pointing upward, so that's going to be a positive 20 kilonewtons sine of 45 degrees. And then when I go ahead and I do the calculations and add that up, and I'm going to get that the y component of the resultant is 39.14 kilonewtons. And once I know the components of the resultant vector, I can draw them in space and then assemble the right triangle and calculate the magnitude and direction. So what's usually helpful here is to actually draw the triangle based on the component. So here I'll use purple again, and let's see, the x component is 29.16 kilonewtons pointing to the right. I'll draw the x component first, and the vertical component is 39.14 kilonewtons pointing straight up. And again, by the parallelogram law, if I assemble the parallelogram, which is just a rectangle, then I know that this right here is the total resultant, FR, and the magnitude of this resultant is the square root of some squares of this right triangle. Resultant is 48.75 kilonewtons, and the angle relative to the horizontal would be from an inverse tangent, opposite over adjacent, 39.14 over 29.16, and this would tell me it's 53.3 degrees here. And so I could write my final answer as FR is a vector with a magnitude of 48.75 kilonewtons at an angle from the horizontal of 53.3 degrees. And this would be the resultant or equivalent force system that has the same external effect of what I was given. So this is considered the scalar approach. If you wanted to pursue the vector approach, that after we've broken up the vectors into components, we're going to actually write each vector in Cartesian vector form. That means like, I hat, j hat, and then we'll solve the magnitude and direction if we need it. So what does that mean? That means we start from the schematic with broken up components here. So after I've broken them up into components, F1 will be 50 cosine 30 I hat plus 50 sine 30 j hat, like this, and f2 would be 20 cosine 45 I hat, and there would be a negative here because we're pointing in that negative direction, or the negative I hat direction, plus 20 sine 45 j hat, like this. And that would be my two force vectors in Cartesian vector form. And so next I'm just going to sum the force vectors together. Here Fr is the sum of all the forces. And when I write this out, F1 is 43.3 I hat plus 25 j hat, and F2 is negative 14.14 I hat plus 14.14 j hat. And, I'm going to sum up all the I components together, and I'm going to sum up all the j components together. Yes, and this will tell me that Fr is equal to, yes, like that. And this is technically a vector answer, has magnitude and direction involved. If I want one number, if I want to answer in the same form, you could draw it in the vector triangle form like this. Here's 29.16 going horizontal, and then the vertical component, or the j component, going like that, like this, 39.14 kilonewtons vertical, and here, this would be my total resultant here. There's my vector triangle, and again, if I wanted the magnitude, I could again just do square root of some squares. If I wanted the angle here, I could just do the inverse tangent, all the same as before. Alright, let's try another example, this time with three forces, and I want to find the resultant, which is the sum of all the forces that are applied here. I've got this concurrent force system. This is what it looks like. Acting on this pin, I've got a force 100 newtons. I've got F2, which is pointing straight up, 180 newtons, and F3, which is pointing kind of down and to the right at an angle of 60 degrees from the horizontal. Whoa, that's pretty steep. 250 newtons. This is our schematic, and we're going to choose X as going positive to the right and Y as positive upwards. And we chose the origin here at the concurrent point. And so just as a friendly reminder, our approach, the first step is to draw that schematic and establish a coordinate system. We have some geometry. This is 60 degrees, and again, this F1, we're given a triangle relationship, a rise and run relationship, if you will. We're given a 3, 4, 5. It's going 4 across, 3 up. Giving this triangular relationship is the same as giving an angle, and in fact, it actually simplifies our calculations. But for those of you who've never dealt with that, we'll see how to deal with it this time. As a friendly reminder, here is the approach. We've drawn that schematic. We're going to break up everything into force components. I'll apply the scalar approach first. We're also going to do the vector approach. Scalar approach, vector approach, doesn't matter. Whatever fits your brain the best is the way you want to go. I will say that once we get into three-dimensional problems, the vector approach is probably going to be the better way to do it, just so that we're able to keep things straight. Sometimes it's hard to visualize the 3 dimensions in just a scalar way. Let's go ahead and break up all the forces into components. And again, that just means creating a vector triangle for each force. And in the Cartesian coordinate world, hey, it's just a right triangle. So check it out. So we'll deal with F1 first. I'll use the color purple. I have here the vector triangle starting from its tail. We'll go across. Here would be my vector components. Boom. So here we're going to use this 3, 4, 5 triangle to figure out what the length of the sides are for F1. We want to know what is F1x and what is F1y. We can do this purely by ratio. If I know here this is 3 and here is 4, and if I have a right triangle and this is the hypotenuse, I know that c squared is 3 squared plus 4 squared, which is 9 plus 16. This is 25. And this is c squared, and the square root of 25 is 5. And that's why I know it's a 3, 4, 5 triangle. I could calculate this angle if I wanted to. I could say, hey, what's this angle theta? And I could say, hey, theta is tangent inverse of 3 over 4, which would give me 36.9 degrees. If I'm more comfortable with using the angle, I could go ahead and use the angle instead. Here, I know that this is 36.9 degrees. I could use this angle to calculate f1x, f1y. But check it out. Let's say I don't want this angle here, and I use this as the angle theta, which is the same as this little triangle, this 3, 4, 5 angle theta. I know that sine theta is equal to the opposite, which is f1y, over the hypotenuse. And in this case, for the large triangle, that hypotenuse is 100 newtons, which is equal to sine theta here would be 3 over 5. And so what I'm using is this ratio relationship to say that f1y is 3/5 times 100 newtons, which is 60 newtons. To find f1x using this 3, 4, 5 relationship, I would say, well, cosine theta is f1x, the adjacent over the hypotenuse of 100 newtons, and that's equal to 4 over 5. And again, I'm using this ratio here. If I solve for f1x, that's just 4/5 times 100 newtons, which is 80 newtons. And that's how I use this 3, 4, 5 relationship to determine the sides of the triangle. F2 is only pointing straight up, so no need to break it up into components. It's only 180 newtons pointing straight up. 0 in the x direction. F3, I'd have the angle 60 degrees. From this right triangle, I know that F3y is 250 newtons sine of 60, which is 216.5 newtons, and F3x is 250 newtons cosine of 60, which in this case is 125 newtons. So I know the length of all the sides of my triangles. I've broken it up into components here. If I'm choosing the scalar approach, I'm going to sum my forces in the x and y to determine FRX and FRY. So to get the x component of the resultant, I'm going to sum up everything in the x direction. Anything horizontal that's pointing to the right is I'm going to consider positive, and that's going to be F1x, which is 80 newtons, and F2x, well, there's no horizontal component for F2, so I'll ignore that, or that's like adding 0. And F3 has a horizontal component of 125 newtons, also pointing to the right. And so I would say FRX is 205 newtons, pointing to the right. Then, now I'm going to do the same thing for everything in the vertical direction. So I look at all my arrows. Any y component or j component pointing upwards, I'm going to say is positive. And so I look at F1. F1y is 60 newtons pointing straight up. So boom. F2 is 180 newtons pointing straight up. So I'm going to add a boom 180 newtons here. And then F3y is 216 newtons, or 16.5 newtons, pointing straight down. So that is negative 216.5 newtons. And when I sum all that up, I'm going to get a result of positive 23.5 newtons, which is the same as FRY is going to be 23.5 newtons pointing upwards. Like, I know the components of the resultant force, and so now I can just put it together to determine magnitude and direction. You know, I like to make a little sketch here. So let's see, I know the x component is 205 newtons horizontal, relatively speaking, a very small vertical component, FRY pointing up. And this is my vector triangle for the total resultant. And here is FR, and the magnitude of FR, the square root of the sum squares, 206.3 newtons. And this angle here, which I'll call phi, is the inverse tangent, which is 6.54 degrees. So I have magnitude and direction from a horizontal. If I want to put it all together in a final answer, I would say that FR is a magnitude of 206.3 newtons at an angle relative to the horizontal of 6.54 degrees. Yay! All right. So that's one way to do it.